rule computing. So how about we do one more, and we call the end of this evaluation. So I want to do this example. I have f of xy is equal to y log of 7x plus 9y. So what is your name again?
Amanda.
Amanda, okay, Amanda. So I want to do partial derivative with respect to x. What do we have?
You think, so for this, it's x is the
Real variable,
okay.
y
And
is
so
the constant. So
Okay, so that's just the 1 over
1 over
y.
you have to put everything, right? So first of all, y is the constant. Taking the derivative, you have to keep this with you.
Yeah,
Right.
so it'll be
1
yeah, it's 1 over
over
7x
7x plus
plus
9y
But then
multiplied by multiplied by the derivative of inside with respect to y, just 7. Am I right?
Yeah.
7. So in the end, you're getting 7y divided by 7x plus 9y. Pretty simple. It's just a matter you need to have your single variable calculus, all the toolbox ready, right? All the functions, cosine, sine, trigonometric functions, logarithm functions, exponential functions, rational functions. You have to have this toolbox ready, and then you have to apply product rule, quotient rule, and we're using this chain rule in place of it, right? So we're taking the derivative, the whole thing, and then going inside. So these are the application of chain rule, in fact, even though I didn't really say it right here. So you need to use chain rule as well. Okay? So still, Amanda, I want to do partial f, partial y. What do you got?
Well, this would be y, this is product rule, right?
Yeah, product rule.
So this is y times 1 over 7x plus 9
Uh-huh.
times, let's see, so 9?
9.
And
Okay.
then plus the natural log of 7x plus 9y times 1.
Times 1. Okay. That's times 1. That's our product rule. So in the end, we have 9y divided by 7x plus 9y plus log of 7x plus 9y. And then, even though we didn't do any evaluation for these two examples, I can give you values of st, then you plug into the formula, and then I give you values for xy, you can plug in the formula to do some evaluation of the partial derivatives. Any questions? So only one remark. Even though I have two partial derivatives for a function involving two independent variables, but this principle is applicable to all the functions with multiple variables. I can have 3 variables, I can have 4 variables, I can have any number of independent variables. And when I do the partial derivative with respect to one of the variables, I will follow exactly the same principle. So if I have w is equal to f of x, y, z, in this case, I have 1, 2, 3 independent variables, okay? And then I can define a partial derivative with respect to x, with respect to y, with respect to z. And the principle is still the same. The computation is still single variable calculus. When I do partial derivative with respect to x, I'm regarding y and z are constants. If I'm taking the derivative with respect to y, I'm regarding x and z are both constants, and similarly for z as well. Now see me? So as long as you know how to do partial derivative for 2 variables, you should be able to do this for any number of variables. So as long as you have 1 variable, whereas the real variable, all the other are just constants. Now with me? So I can indeed have f of x1, x2, x3, n variables. And then we can define a partial derivative with respect to x1, with respect to x2, with respect to xn. When I do this, the principle is follow single variable calculus. So I will give you one more example so we can go a little bit more involved. So I want to have a function, let's say f of x, y, z is equal to 3 minus 8xy squared minus 5z to 4. Okay? So this is the function involving 3 variables. So I think Kelly, all right? So I want to compute partial f, partial x. What do we have?
Okay, so you take the partial with respect to x.
Mm-hmm.
So it's just negative 8y squared.
Negative 8y squared, all right? 3, people agree? 3 constant, and y constant, z constant. So this derivative vanishes, this derivative vanishes. Only this term is gonna contribute when you take the derivative with respect to x. And y is the constant, so you're just getting the coefficient of x, okay? So still carry partial f, partial y. Negative 16 xy. Still derivative with respect to y, all the other things are constant. So these are all vanishing. So only the middle term is contributing for y. And very last, the partial f, partial z. This guy is equal to minus 20 z cubed. Okay? So the computation for partial derivatives is the same for all the multivariable functions. Okay? Next, as I promised, I want to put this into geometry. So one thing I want you to keep this in mind every time we talk about the calculus. This calculus is study of change. All right? You have to have this dynamic in your mind. Change of what? If I have a function y equals f of x, I only have one independent variable and one dependent variable. It is independent, so you can change independently. It is a dependent variable, which means as x is changing, y will be changed accordingly. All right? So calculus essentially, in terms of derivative, it is studying the rate of change. So rate of change. In other words, if I'm evaluating the derivative at a given point x equals a, so this guy will be equal to f of a plus h minus f of a divided by h. Okay? So what this means is I will change my independent variable from a to a plus h. All right? So the independent variable originally is a, after the change is a plus h. So how much do I change? Exactly h, all right? And the change of the function value is the difference between the function value after the change and before the change. Are you with me? So this is essentially saying this is the change in y and then change in x. And the derivative is talking about the rate of change in a limit. So when h goes to 0, and this quotient as change of the dependent variable over the change in the independent variable will be our definition of the derivative, right? And translating it back into the curve, this one will be talking about the derivative, the slope of the tangent line at this point. And then if you all remember the small triangles we have, right? So if you are approaching this point, the change in y is in the vertical change. Change in x is the horizontal change. And then when you approach this point, taking the limit of h goes to 0, that's exactly talking about the slope of the tangent line, all right? So that's the basic geometric explanation of what we have. So this is dot of y, this is dot of x. When these neighboring points are approaching to a fixed point A, this quotient is going to define the slope of the tangent line here. Okay, all on board? This is the first principle for partial derivatives. Now I want to translate this into multi-variable case, especially two-variable case. So one complication immediately comes up is I have two independent variables. So this is my independent variable, and I'm at a fixed point AB. Okay, I have this function z equals f of xy. Right. So as usual, x and y are my two independent variables. Z is the dependent variable. So x and y can change freely, and z will be changed accordingly if you change your independent variables x and y. One very different thing happening in change of the independent variable here comparing to that case is if you're in a one-dimensional case, you only have one variable x. You can increase it by h, you can decrease it by h, but that's pretty much all the things you can do. Are you with me? So if you still remember our Mendes class, the change in x, y is much more diverse. If I'm at AB, I'm going to change my independent variables x and y. I can move to all the neighboring directions as I can. Are you with me? Change in the independent variable essentially is saying you are making this point moving. In a one-dimensional case, moving the independent variable is just left and right. But in two-dimensional, you have all kinds of different ways of changing the independent variable. You can move in the x direction for small amount h. You can move in the y direction for a small amount of h. You can indeed move to any other arbitrary direction you can choose for a small amount. When you do that, coming back to the surface, the function will be changed accordingly. For instance, if I follow this direction, I increase my x value by h. What is the terminal point I got? If I only increase my x value by h, I keep my y value the same. So a plus h, but I'm having a b in the coefficient. So right now I have this as my new point after change. So if I go back to the surface, the function value will be changed from ab to f of so this is f of a plus h and b. Okay. So if I choose my direction to be x direction, I can change my x value by a small amount. My function value will be changed accordingly. So you can define a rate of change. Am I with me? The rate of change will be if I follow x direction, I change my x variable by h, and my function value will be changed by some amount. So I'm still taking this portion, which is limit h goes to 0, f of a plus h b minus f of ab divided by change of the independent variables. Still, because b is kept the same, and x is changed by x. So this is, I'm sorry, x is changed by h. So this is essentially still change in the xy. Because of the points are moving, the function value will be changed accordingly. So this is the function value after the change. This is the function before the change. So this is the change in z. So if I'm taking the derivative of h goes to 0, this one will be exactly, making a guess, you only have two partial derivatives. This one is exactly partial derivative with respect to, which one is changing? X is changing, y is kept fixed. So it has to be a partial derivative with respect to x, evaluated at given point AB. Okay? That is the essential definition for partial derivatives. Partial derivative with respect to x. In a computation, we're regarding y as a constant. In geometry, that's exactly the same thing because y value does not change. I'm only changing the x value. And then this partial derivative is talking about a rate of change. Now I want you to put this number, for instance, if I compute the partial derivative with respect to x, evaluate at AB is equal to 20. 28 or something. If it is equal to 28, what does this number tell you? What does this number tell you?
The rate of change.
It has to be a rate of change, but also I want it to be a slope of something. slope of a line. Any line you can have, right here. Is there a line right here? This is the line, right? If I'm following the change in the x direction, I can have a continuous curve on the surface when y is fixed to be value b, x is changing around a. So I will indeed have a whole curve passing through this point, which is parallel to x-axis. Are you with me? This is how you can get the curve on the surface by keeping y fixed, but only x is changing. In fact, this curve is the intersection of a plane parallel to xz plane with the surface. Can you imagine that? So if this is z, this is x, I can have a whole plane cutting through the surface, which is passing through this point and parallel to xz plane. I can also have this intersection between these two surfaces, right? Which is essentially saying the same thing. Your x is fixed. I'm sorry, your y is fixed, x is changing. So indeed, even though I have a two-dimensional object, by restricting y value, I have a whole curve right here. And because you have a curve, you have a tangent line, and this 28 is exactly talking about the slope of that tangent line. So if you have a tangent line from this curve, okay, and this partial derivative is exactly talking about the slope of a tangent line to the intersection of the surface with xz plane. Okay, I'm going to say it again. So this number is talking about the slope of the tangent line to the intersection or to the intersecting curve of a graph with a plane. With a plane that passes through AB and is parallel to XA plane. Even though it's a multiple, but in the end, geometrically, it's a pretty simple object.